Yeah? Okay. So what I like about this topic is that you really did cover most of it last year already, and there's only a couple additions with derivatives and integrals in order to add on to the material that you already know. So chapter 7 is about work, and then chapter 8 is about energy. We're going to put those together, work and energy. We're even going to take a look at momentum kind of with it, because the work, energy, and momentum problems go together. And we've seen that a couple times already. Last year in your class, we talked about elastic versus inelastic collisions, where momentum is always conserved, but sometimes energy is not. Right? We lose energy in the collision. So let's start with a quick, simple demo. And you may have done this. Donachek made a demo last year. I don't think I did in my class. So this one's really basic. So let me show you what I mean. Have you done this before? In Donachek's class, actually, maybe you guys do this? You would recognize it right away. You may have done it.
You dropped this time.
Yeah. So for the case of the circumstance, this is not very pumped up, unfortunately. So it's not really bouncing too far off the ground. So the more pumped this would be, actually the better it would be. But there are two basketballs next to our both like this. Unless there's one over there. Now the second is just a squishy T-ball. It's not a regular baseball. Purposely the squishy one. Actually, it wouldn't matter for baseball in this case. This, though, you want to have a little more pressure. So if these two objects collide, when they collide, it's easy to see actually. They're deformed, right? You can see the deformation occurring. And if you look at a basketball being dribbled in slow motion, it deforms every time it hits the ground. So both of these objects have mass, so therefore both of them have energy. From a given height, they have what kind of energy? From a given height? Potential energy. And when as they fall, they gain kinetic energy. Very good. Now, when this, let me actually drop them so I can show you real quick. 1, 2, 3. So where did the little acceleration on the T-ball come from? Where did the acceleration come from on there? Okay, bounce back force of the ball. Any more physics terms?
The ball compressed, it exerted more force going up onto the baseball. I don't know,
That's a great example. Right? The ball compressed, which acts like a spring, right? Because it compresses or expands, and then it exerted a force on the baseball. Very good. That's exactly right.
I do the same thing with a tennis racket. If you put a ball in the racket and drop the racket, then the ball shoots up and you can hit it.
So you drop the racket straight to the ground, and when the ball hits the racket, it pushes on the strings, and then it launches off. Yeah. And you can do this with 3. It's a lot tougher, and I might even send you guys or show you a video of it, because you have to have a mechanism that drops nicely. But you can do it with 3 objects as well. And what will happen is each time you add another object, you'll increase the amount of energy being transferred into the smallest object. Because now it's 2 objects, elastic energy, that's being converted into kinetic energy. So the key here is that we have to recognize we have different types of energy, right? So you already said we've got potential energy that's a function of height. Some books call that gravitational potential energy, because gravity is what gives it energy. You have the energy of motion, which we're calling kinetic energy. And then you have the energy of position or state of being. And that position or state of being is elastic energy. Okay, so let's write down formulas. The first one, and this should be a review for these formulas to start. Then I want to get into where you're going to see this. So the first formula we're going to look at again is potential energy that's gravitational. Some books call it capital U, and that's simply mg delta y. And that's if we want to see the change in potential energy. If we want to see what the current potential energy is, we can just do mg times y to get the energy at that height. Again, this is for change in potential.
This is chapter 7.
This is chapter 7. Yeah, we're going to put 7 and 8 together, though, because 7 is kinetic energy and work, and then 8 is potential energy, so we're not going to split them up. Kinetic energy here is going to be a function of velocity, and that's 1/2 mv squared. By the way, potential energy is usually delta because there's usually something falling, right? That's why I'm putting the delta there. Yes, again, we can find the potential energy at a given moment or a given height by using mgy. Kinetic energy is usually the energy at a specific moment because we're trying to find the velocity at an instant. So we see that we use kinetic energy without the delta. When we have a delta there, though, we'll talk about where that plays a role with work. And a lot of you remember the work kinetic energy theorem that plays a role. The third type of potential energy that is elastic is 1/2 kx squared. Now, we have not talked about springs yet this year. So this is our introduction or our quick blurb about springs and going back to Hooke's law and describing Hooke's law. So we already talked about forces in chapters, 4, 5, and 6, I think, all 3 of them, or 5 and 6. And what we ignored or didn't talk about is Hooke's law. So let's write down Hooke's law at the top here. And Hooke's law tells us a force stored in a spring is equal to negative kx. Yep, it's not squared. Negative kx. Very similar formulas, right? Very similar formulas. And in this formula for the force in a spring, x is really delta x here. So if we want to call that delta x instead, this is one of those cases where we're looking at how much the spring stretches or compresses by. How much does the spring stretch or compress by? So the delta indicates that the spring is physically stretched or compressed.
K is the spring coefficient.
Yep, spring constant. Spring constant. So K can be called the spring stiffness, the spring constant, the spring rigidity. Any of those words are fine. I don't know if coefficient's been used, so be careful with that word. But yeah, spring constant really is the word. Why is there a negative sign there in front of the K delta X? You remember that?
It's compressing, so when it stretches in the positive direction.
So give me an example. So say this is the spring, right? And you stretch the spring.
That'd be positive.
Delta X is positive, yep. So which way is the spring going to pull though?
You would pull it inwards.
The spring pulls back against the way you pulled it, which is why there's a negative there. So think about that again, all right? So this is your spring right here along this meter stick. It starts first as the length of this marker. You pull on it, which gives it a positive delta X. And then as a result, the spring pulls back in that direction, which is where the negative sign comes from. So whichever direction you push or pull on a spring, the force is exerted in the opposite direction. That's where the negative sign comes from in this formula. So this is Hooke's law. And Hooke's law allows us to figure out the spring constant. There's a good chance on an AP exam that if the problem is, say, 4 or 5 steps long, and they don't give you the K value, they'll give you an amount of force being applied to a spring, the delta X value to solve for K, and then that K could then later be used for your potential energy elastic problem. Okay, so a lot of the time you solve for K in Hooke's law. Matt?
What is the X in the potential energy?
It's the same thing as the other X. So if we want to call that delta X, we can do that as well. Yep.
And that's just how far the spring is stretching.
Or stretching or
Or compressing.
compressing. Always either or, right? So notice the delta X in this formula. Does it matter whether it's negative or positive? Why not? It's squared, right? So no matter what, for potential energy in a spring, we know that we're squaring the delta X. So whether it's compressed or stretched, the energy stored is a positive amount of energy. Okay? So that's the only thing we really look at with negative energy. It's the one main thing that we think of as negative energy. Where's energy sometimes lost? Because we're like, oh, energy can't be lost nor gained. That's mechanical energy, right?
Collision.
In collisions, this occurs.
You have a heat beam generator?
What is it?
Heat beam generator?
Yeah, thermal energy. Some sort of frictional energy is where we have a negative energy amount. And we'll see that with the work kinetic energy theorem, because if we know an object is moving this way, which way does friction act? Well, it acts this way. And that's an angle of 180 degrees. And the work kinetic energy theorem, or work, is Ft cosine theta. Cosine of 180 is -1. So really, thermal energy or frictional energy is where we'll have a negative energy. And by negative, I just mean energy loss. Okay?
So it could be positive too, right?
What's that?
Thermal energy.
Could thermal energy be positive? The work done by friction could be positive for rolling friction. That's the one circumstance we're going to talk about that with, for rolling friction. Okay, so the last formula to write down is the formula for work. Work equals F times D times cosine theta. And this is the one that we're going to really focus on for a little while, because this is the main one that we can use a little bit of calculus for. Okay, and this is where it's going to be applied on your AP exam. So first, your text starts with the concept of kinetic energy and motion, and then they go into like the concept of work and how you can get things moving. And think about it logically. What's the only way you can get this eraser moving? By applying a force. So the only way to give this object kinetic energy is by applying a force. And a force means that you must have done some work. So there's a connection between work and kinetic energy, and that theorem is called the work kinetic energy theorem. And that's in red at the bottom. Okay, and if you want to, I don't recall, you guys can check the formula sheet. I don't think you're given all of these formulas on your formula sheet. So start to recognize again, right, as we talked about this throughout the year, what formulas you need to memorize as opposed to what formulas will be given to you. Okay, so take a look at that formula sheet if you need to see which ones you want to maybe circle or which ones you want to write down and memorize next to it. I would think that by this time from last year's course, you have, let's see, you should have really this one here, this one here, this one here known for sure. Maybe this elastic energy one you still have to memorize, but because Hooke's law and the elastic energy are so similar, it's not that bad actually. And can anybody see the connection now between elastic energy and Hooke's law?
K delta X is substituted for the MV, and then
K delta X
K
is...
delta X is substituted MV into half MV squared.
That makes it similar, but I'm asking the direct connection, sorry, between these two formulas right here. The direct connection between those two. And I ask you this year, not last year, as my hands. I'm asking you this year. Last year you would not have been able to figure out that connection.
It's like slope, like the inverse. I just remember, like, isn't it kind of similar to the...
It's the derivative.
Yeah.
Slope, derivative.
Yeah.
Look at the derivative of this. What's the derivative of this come out to be?
K
Comes
delta
out to be
X.
that, without the negative sign. Without the negative sign. I see that that's missing, right? But take the derivative of this. Bring the 2 down in front. 2 times 1/2 cancel. You're left with kx, or k delta x, which is that. So it turns out that the derivative of your potential energy elastic function is Hooke's law. That's where Hooke's law really comes from. Now, the question which came first, I don't really know. But maybe they go Hooke's law, took the antiderivative or integrated it, right? And got potential energy function for their elastic energy. But there is a connection there. So recognize that, okay? So this is derivative. If we're going derivative, if we're going that way, and then if you use the phrase integral, or is it just antiderivative so far?
Both.
You've heard the phrase integral at least? You've said it? Okay. So depending on which way you're going, right? You go from one to the other. So there's one connection for calculus for this. Second connection. Your work done. And this is the one that's a little bit trickier. If I apply constant force to something, then F is some value. And I can say to myself here, actually I'm going to start a new slide for this next one. Okay, I'm going to go to the next slide if anyone hasn't written anything down in here. And I'm going to take a look specifically at this formula on the next slide. Okay, that's the one that's going to matter a lot. So let's take a look at this. And let's take a look at F. Okay, we've got force and we've got distance. The y and the x-axis. If the force applied is actually constant in the problem, and we want to find out the work done, it's pretty simple actually. So let's draw a function that looks like this and call this force F0. And let's say we've got D0 right here. So we've got some applied force over some distance D0. If I want to figure out the work done, thanks to the work formula FD cosine theta, I can recognize that really this is just FD, and then the cosine theta comes in to play a role if the force is applied at an angle. But let's say for the circumstance here that it's applied as a horizontal force, so the cosine of 0 is just 1. That's not going to matter in the problem. So again, I'll put a diagram so if it helps maybe. Okay, there's my diagram. And here's what's happening. The object is moving from there to there. Okay, and we'll call that distance D0. So this object is moving. Notice, by the way, I started and ended at the center of mass. In the AP exam, that is important. If you show some sort of diagram of motion, beginning to beginning, or center to center, or end to end. But you don't start at the beginning of one object, or the object, and then draw your displacement vector at the end of that object, because then you'd be adding in these extra distances right here. So let's just keep that in the back of our mind for diagrams. Now for this problem, what we'll notice is that this force is applied over distance. Cosine of theta is really cosine of 0, which is 1. So if I want to figure out the work done, it's simply F0 times D0. It's F0 times D0. So make the connection to calculus now. What are we really looking at? If it's F0 times D0. what are we really looking at? And use the graph if it helps you here. F0 times D0.
Is that like f of x times dx, essentially?
Essentially, yeah. It's like the function f of x times dx. Now, in this case, we don't have a small, infinitesimally small width dx, right? So we will get to that in a second, but more generally speaking.
Wouldn't that be the integral?
Yeah, which is f of x times d of x. So specifically in this diagram, what shape are we looking at? Yeah,
Yeah.
shade in, right? Take a look at this area right here. That area, well, what's the height of the function? The height of the function is f0. What's the width of the function? d0. So if I multiply f0 times d0, I'm getting the area under the curve. So it turns out that work is really the integral. The integral. So with a constant force, this problem is really simple, and this is it right here, with a constant force. But now, if I take the same application or the same scenario, take the same scenario and instead I draw a force function. Okay? I cannot call this f0 anymore. I have to call it some function of x, or actually in this case, some function of d, if I'm using d on my x-axis. Which would be kind of odd because you guys used to dx, it's going to be dd. Follow what I'm saying here? Okay, we're not looking at x, we're calling it d, this axis. So if I look at this problem here now, I cannot simply find this area using geometry. It's not a rectangle anymore. I can't just say, oh, it's force times distance. But it still is force times distance. It's just that now, when we find the work done, it's the integral from the beginning position, which in this case is 0, to the ending position of the force function times dd. Now, I think your book is probably going to use f of x times dx, so I'm going to change that. Let me just take a look. I think they're going to use f of x times dx. Here we go, variable force. Yeah, they're using f of x times dx. So to be consistent, change this right here. You can leave d0 there, that's fine. But let's call this other stuff instead dx. Okay, so I'm changing this to call this the x-axis, really. And I'm calling this dx. And makes this right here also, this d, makes this f of x. But my limits of integration, have you guys done the limits of integration from like 0 to 5, you integrate with the numbers at the bottom and the top?
Yeah, we're pretty full.
Okay, so because I know you were talking about the average value theorem on the right, so I'm thinking you guys had done this already.
This is before integrate.
Perfect. Perfect. Okay? So really what we're doing is we're finding the area under that curve from 0 to d0, to whatever point we stopped at. So this is where we're going to be seeing the work kinetic energy theorem applied. So this is the work done, and this is equal to delta KE. It's equal to the change in the object's kinetic energy. So if a problem gives you a variable force function, write that down here at the top of this. This is a variable force function. This is a constant force function. When a problem gives you a variable force function, and that means that here's what's happening. Ready? Watch me do it. I push hard, slow down, push harder, push faster, slow down, push faster. My force is varying. It's changing. I can't find the work done. I could, what can I do? I can use Riemann sums, right? And I can break this into a lot of little linear functions and piecewise functions and find all those areas of trapezoids. Have you guys done trapezoidal method or just rectangles, right? Yeah, whatever it is, rectangular, trapezoidal, because trapezoids work really well, by the way, for integration. You learn that in the college calculus. So I can find all these little polygons and estimate, but I don't want to do that because now you know calculus, right? I don't want to estimate that area. So we use this formula here, okay, from the beginning to d0. I'm calling d0 some arbitrary distance. Your book says go from x0 to x, meaning from initial to final, right? Initial position to your final position. The AP exam likes to give these problems as part 1s. You'll see that a lot, not part 2s. If they're in part 2s, it'll be obviously a sub-part of the problem. But this is a very useful multiple choice problem where they give you a force function, you're given the graph or you're given the actual function itself, You can integrate it by hand or on your calculator, which I would absolutely integrate on the calculator. If you don't know how to do it yet, we'll go over that. 100% integrating the calculator in this exam, unless it's part 2 where you have to show some work. And then what it'll do is, it'll be like, well, that's the amount of work done. Determine the change in velocity of the object. And that's where you have to set this now equal to the delta KE, the kinetic energy change. So a lot of the time, we look at the work kinetic energy theorem, and we say, yeah, work equals delta KE. Well, the work that we might end up using would probably be this formula right here that goes in for W. That goes in for W. What else? That's the application for work. I want to also talk about the application for power. Just see if there's anything I'm jumping through. What I'm trying to do today is kind of cover the stuff you've done last year, but also give you like a twist, right? So you see where the calculus knowledge is applied to. Oh, Wandell was that? Is that Chris? Is that?
Yeah.
I didn't realize that. Okay, this is Chris. All right. So we'll look at power now. I want to make sure I'm not forgetting anything in here. Gravitational, good. Good. By the way, your book derives how you can take Hooke's law and integrate it and get 1/2 kx squared for the elastic energy. It means literally just an integration, which we already saw. But if you wanted to see it done algebraically, you can. Let me show you one quick. This is probably pretty important. Not that you need to be able to do it on the exam, but so you understand where it comes from. So we started here a minute ago with work equals the integral, and the book is using x, 0, and x. So I'm going to use those for the moment. F of x dx. Now, really, if we look at this, this is really the integral from x0 to x final of force. And force is really ma. So your book starts by replacing force with ma. We did this last year in my course. We didn't use integrals, so you might see some similarities. And we're just going to come up with the kinetic energy work theorem. Let's see. Your book then says the following. We could say this here, ma dx, is the same as m dv dt dx. It makes sense of that. This is really m times a times dx, but a is the derivative of velocity with respect to time, because that's your acceleration function. So replacing that with dv dt. Let's see. Okay, we can write a side note, and this is the chain rule. You guys have the chain rule down pat by now? The chain rule, think about dv dt and what it really is. dv dt is really dv dx times dx dt. And think about that logically. The dx's cancel, right? This is actually just algebra, even though it's derivative chain rule. It's just algebraic cancellations of dx. So you could probably expect what we're going to do here for the next part. So we could take, let's see, this is going to be ma times dx still. And this is going to be, this function here is really v. Right, take a look. This dx dt is really v, if you think about that logically, because it's the derivative of position with respect to time. So I can replace this dv dt with this entire expression here. So I'm going to take this expression and replace it in for dv dt right there. So we've got m dv dx times v times dx. So again, I'm replacing dv dt with dv dx times velocity, which is right there. And then we can notice what happens here on this side. The dx's both drop off in this case. So this formula becomes ma dx equals m dv times v. These dx's cancel right here and here. We're going to nicely rearrange it and move the v over. All right, we'll move the v over to the left, to the front as a coefficient, or as a, not a coefficient, sorry, as an integrand before we integrate. So I'm going to just rewrite it. I'm switching v and dv. All right, switching these two right here. And now at this point, what we'll notice is that we can look at this problem and recognize that this can be integrated. This part, or this problem here, can definitely be integrated. And what's interesting to notice is this. On the left-hand side, if we were to integrate this, this becomes the integral from x0 to x of ma dx. And this becomes the integral. And on this side, we're going from a starting velocity to an ending velocity. So what are my limitations going to be? What are my limits going to be for the next one over here? What am I going to write instead?
V0 to V.
Yep. From v0 to v, some initial velocity to final velocity of mv dv. Well, we already made a statement earlier, and we've got to go back to the beginning to see it, that this is work, right? So this whole thing that we've been deriving is really work. That's all it is. So we could replace this entire integrand on the left with work by definition. This is just work. And on the right-hand side, what does that integrand, or what does that integration yield? What's the integral of mv going to be?
1/2 mv squared.
1/2 mv squared. Integrate, right? Raise this up by 1, makes it squared, and divide by that new 2. You've done the integral for the power rule by now, for sure. So v is your variable of integration. So when we integrate this, this becomes, again, raise it up to a 2, right? And then divide by 2. I'm going to erase that in a second. But that's what we're doing, right? We're going to raise it up a power and divide by the new power. That's the power rule. So it's going to be on the next line. We're going to write that. mv squared over 2. And what are my limits of integration? From v, 0 to v. Okay, from v0 to v. I was running out of space, so this is what she wanted to do. Okay? And then what do we do with those limits? According to the fundamental theorem of calculus, what do we do?
Subtract the second one first.
Yeah, you subtract the second one applied in here from the first one applied in here. Very good. So really, what does this become as a result? This becomes work equals mv squared over 2 minus mv0 squared over 2. And there's the work kinetic energy theorem. Work equals change in kinetic energy. Final kinetic energy minus initial kinetic energy. Okay, final minus initial. So that's the derivation of the work kinetic energy theorem with a variable force function. Last year I did it with a constant force. We got the same result. We got W equals delta KE. And it's the exact same thing here again. Except now we used integrals to come up with that knowledge. Okay.
Another question.
Yeah.
Where do you, how do you get dv over dx times v? Like, where did the v come from?
Up here in the top right.
Yeah.
So what's dx dt? The derivative of position with respect to time. Remember this?
Yeah.
That's velocity by definition. So instead of using dv dt, we broke it up into dv dx, which is this, times dx dt. Because Matt, watch what I'm going to do. Look at the top right there. These dx's cancel, don't they really?
Yeah.
So isn't this still just dv dt, which is what this is?
Yeah.
So instead of using dv dt, we replaced dv dt right here with this expression, which is really this expression, which is why I'm saying that goes in for dv dt, which is where this comes from right here. So it's substitution method. I'm replacing dv dt with dv dx times v. It's a lot of dv dx in that statement, but you should be used to that by now from calculus. You should hear these phrases a lot.
What is so dx over dt is velocity, but what is what is dv over dx? Like what is that?
That's not actually anything that we know. It's the derivative of velocity with respect to your position. It's not another function that we've actually derived. It's the only reason we've done it is to show the cancellation of dx, the differentials. Remember, differentials apply, the rules of differentials are algebraic. Right? Keep that in mind. Differentials are just like variables. They're algebraic in nature. So still, they do cancel. So all we did for that reason, Matt, was to cancel the dx there. This is not an actual thing. It's just that we applied the chain rule of calc to come up with what
This is
ddt
just-
is.
This is just proving the work.
That's all it is. Proving where the word kinetic engineering comes from for a variable force, right? For a variable force in this case. So in the end, this is still the integral of f of x dx. That's what this is, and that equals that whole thing.
Can we just do some problems just to apply it?
Yeah. Yep. So let's take a look at one. So your book has a good example of the variable force and work done. So let's take a look at the example itself. This is on page 165. Well, technically it's on the bottom page 164. It says the following. A block slides along a frictionless floor and acts as a force acts on it, starting at x1 equals 0 and x3 equals 6.5. So it's starting at this position of 0 and ending at a position of 6.5. We're told that a force acts on it. As the block moves, the magnitude and direction of the force varies. Not only the magnitude, but the direction varies. So the force is positive, and then suddenly maybe it's negative. So the force is physically going to vary here. Let's see.
Wait,
Says-
where is this problem?
Page 164 to 165. The very bottom of 164 is where it starts. And it's all into 165. It says, for example, from x equals 0 to x equals 1, the force is positive in the positive direction and increases in magnitude from 0 to 40. So let's take a look at that. So from, again, 0 to 1 meter. So here's 1 meter. This is my x-axis here. This is my force. And we're told that it goes up to 40 from 0 to 1 meter. I'll put units on the axis instead to make this easier, okay? Makes life easier, right, by putting units on the axis, not on each tick mark. So we know that it goes from 0 to 40, the force, from the beginning to after 1 meter in distance. So those are my first two coordinates based on this. It says, again, I'll read it. For example, from x equals 0 to x equals 1, the force is positive and increases in magnitude from 0 to 40. And that's what I've shown there with those two coordinates. And then it says, from 4 to 5, the force is negative from 4 to 5. So let me get to that point. We're going to go up to 7, by the way. So if you need to space it out a little bit, maybe I need to space it out a bit better as well. I mean, I guess it doesn't really matter if the spacing is perfect because I'm just sketching this. But I'm going to make this 3. I'm going to make this 4. I know it's not drawn to scale. Just bear with me. Make this 5, 6. Can I extend this? Yeah, I'm just going to extend it a little bit. Okay, I'm going to put 7 out here. I'm going to just move some of these over to make them somewhat of a better estimation here. Okay. Again, those coordinates are not perfectly drawn. But those are the spots that are going to matter based on the problem itself here. So I'm just identifying them. So it says from 4 meters to 5 meters, from 4 meters to 5 meters, the force is negative and increases in magnitude from 0 to 20. So here I have to extend my negative axis here. This is going to be negative 20. And from 4 to 5 meters, I'll use red now, it goes from 0 to negative 20. So I know already that the force is looking like this, and the force is looking like this. Those are the two portions I'm given so far. So I've got my force in the very beginning, and I've got my force function here. So in the beginning, it's like this, right? Light force, more, and I'm accelerating. I'm not just accelerating, because if I'm applying a force, I'm accelerating actually. I am increasing the force applied from 0 to 40. So my derivative of my force is positive, right? It's an increasing function. It then says what? The block's kinetic energy at x1 is equal to 280. So let's jot that down. The kinetic energy, again, at the position of x1, we'll call that 1, is equal to 280 joules. The block's kinetic energy, God bless you, at x1 is 280 joules. And the first question says, what is the block's speed? What is the block's speed at x equals 0, x equals 4, and x equals 6.5. And x equals 6.5. So let me just take a look if they give you the entire diagram. Yeah. So we've drawn in what we know based on the wording. The problem says according to figure 713A. So I'm going to fill in the rest of this diagram so you guys have an idea of how this force is working. But it was good that we did it the first way to show what's physically happening in those two regions. But the rest of the force function looks like the following. From 1 to 3, it's a constant function. Okay? From 1 to 3, it's a constant force. From 3 to 4, it drops linearly to the origin, or to the horizontal axis, rather. Sorry, not the origin. From 5 to 6, it's a constant function. And from 6 to 6.5, it goes back to the horizontal axis. So this is what the figure actually looks like in the problem. The problem, though, gave the wording for the regions from 0 to 1 and from 4 to 5. The other regions were only given in the diagram, not in the problem. So why did we need all those other regions? Because clearly we're going to have to use the areas under these curves. So as a result, we need to know what the height of the function is in these regions. I only knew 4 to 5 and 0 to 1 based on the wording. So the rest of the diagram is absolutely important here. And all we're told again is that the energy at a location of x equals 1 is 280. That's only at this moment right here. Okay, that's the energy we know, only right there. Now, the problem again wants us to find the speed at several locations. So let's start by looking at this. So first it says find the speed at x0. At x0 or x equals 0. And at first you might say to yourself, well, it's just 0, Mr. Howell. There's no force applied, right? So right away, I would personally think this is going to be 0 because no force is applied. It's not moving. But that's not necessarily true. This problem only tells us about what's happening from a certain location onward. It could have been moving previously and then a force was applied. I mean, think about like a running back, right? A running back is running for a touchdown, and maybe a cornerback catches up and jumps on his back. Well, the person has velocity, and then you jump on their back and apply force. So this force could have started being applied when there was motion in the beginning. So don't let this problem mislead you and say, the speed at 0 must be 0 because there's no force applied right now. It could have started with some speed. And the question is, how do we figure it out? We have to backtrack because we know it's 280 as an energy here and figure out what energy it has here.
Regardless of the speed before the speed at that point is like different or it's the same.
At what point?
At 0.
The speed at 0 can be some number. It absolutely can be some number. Because remember, this is distance along the x-axis, right? This is x as a function of meters, or x in terms of meters here. So this absolutely can have velocity in the beginning. Let me show you why I make that statement, okay? How is it possible for the object to have 280 joules of energy right here? Well, what did we say the work kinetic energy theorem tells us? The work kinetic energy theorem says the work done is equal to the change in kinetic energy. Well, the work done is really the integral of the force function with respect to x, and that's still equal to the change in kinetic energy. And where are we going? From where to where? From where to where are we going? From what x position to what x position are we interested in for the first part? For the first part. 0 to 1 meters. So we know the change in kinetic energy from 0 to 1 meters is some value. Well, because it's a triangle, it makes life easy, right? This problem is not given as a force function, they're giving you the graph. So you're not going to actually have to integrate here. Because the integral from 0 to 1 of f of x dx is really just that. That's all it is. It's that area, and it's a triangle. So on the exam, when they give you a graph, and it's a bunch of piecewise linear functions, use triangles, use rectangles. If you want to use a trapezoid, if you need it, use it. You can use a trapezoid here, right? Or you could, like we've done in the past, split this into regions. Triangle, rectangle, triangle. We did this earlier in the year when we talked about the concept of an integral. Okay? So really, what does that area become? The base is 1, the height is 40. Base times height is 1 times 40 divided by 2 because it's a triangle. So what is the area? 20. So it turns out the change in kinetic energy is just 20 joules. But I just said that at 1 meter it has 280 joules. But it only changed by 20. So how many joules of energy did it have in the very beginning, actually? 260. Think about it. Starts with 260, gains 20 joules of energy as a result of this area, and therefore has 280 joules at x equals 1. So this problem is very interesting because it's very misleading if you don't think about your calculus knowledge. If you just say, oh, in the beginning there's no force, so there can't be velocity, it's, again, not correct. So at this moment in time, and we can do this maybe on our diagram if we want to, we could just list the amount of energy it has at any given moment. So this is 260 now, and at this moment it has 280 joules of energy. I'm using yellow to indicate that. And again, it changed by 20 joules. So the question is still not answered though, right? The question has not still been answered. The question says, by the way, the mass is given as 8 kilograms. Let me jot that at the very top of here, because obviously we're going to see that's going to come and play a role. The question says, find the object's speed at x equals 0. So how can we do that now? How can we find the object's speed at x equals 0? Chip, go for it.
Would you do 1/2 mv squared equals 260?
Yeah. The amount of energy in the system, which is kinetic, equals 1/2 mv squared. We know in the beginning it has 260 joules of energy just because it's moving already. Again, this box or block already has motion here. And that equals 1/2 times 8v squared. Okay? So yes, this is a simple plug and chug after you do the calculus portion of it. Okay? So double 260. 520 in this case. We'll divide that by 8. 520 over 8 and then square root it. I'm not really concerned about the number, but let's write it down just to have it. What do we get?
8 meters per second.
Oh, it turned out to be 8 meters per second. Nice. And it was 8 kilograms. And that's going to be V0. Okay, V0. The velocity at a position of 0. So the whole idea here is that the integral of force function gives us work done, and the work done turns into kinetic energy. I'll do it again physically so you can see it, right? You apply force, and it causes motion to happen. That's physically what's happening here. Yeah?
So then is it the same at 4?
Well, let's figure it out. Let's find out what's happening. At 4, what is the overall integral? We have to figure that number out. Remember, the force at 4 is 0, but is the integral at 4 is 0? It would be 0 if it had a positive and a negative area that canceled out, right? Remember we did those problems earlier? You have a function that's positive, and then the exact same function that's negative. Those areas would cancel, wouldn't they? And therefore the overall force, or the overall integral would be 0. So the work done would be 0. You would have all this positive work speeding it up, and then you would have a lot of, if the force is under the axis, what kind of work is it doing? It's opposing motion, so what kind of work? Negative work. So area above the axis is positive integral, positive work. Area below is negative integral, negative work. And think about it logically. This eraser, ready, after 4 meters is moving positively. And then suddenly I apply negative force. I am opposing motion. I am doing negative work. I am now friction in a sense. I'm slowing it down. So at a distance of 4 meters, we need to figure out the velocity. So what I would do, right, is you could do it two ways. You could find the velocity at 1 meter, if you wanted to, with the 280 joules. Then find this resulting area and see what the new velocity would be. But I don't think that makes sense because we're not asked about the velocity at 1 meter. So why find it, right? We know the velocity at the beginning. So let's utilize that knowledge to help us. So instead, let's do this. Let's look at this entire area here. And what is that area going to be? The integral from 0 to 4 of f of x dx. What is that number going to be? Well, I'm going to use trapezoids because I personally like trapezoids. You could break it into 2 triangles and a rectangle, but honestly, it's a waste of time. You're doing math 3 times. Base 1 is 4. Base 2 is 2. That's the top up here. So we got 4 plus 2. We average those bases. So if you're not sure about your area of a trapezoid, it's 1/2 base 1 plus base 2 times the height. This is the area of a trapezoid. So 1/2 times 4 plus 2 times the height of 40. That's going to be half of 6 is 3. That's 120 joules. You've got to be able to do a trapezoid area because honestly, you break it into triangles and rectangles all day long, you're just making the test longer on yourself. And you guys saw already on that mock exam, right? A minute and change per problem. You don't want to have to be breaking it into 7 different shapes when you can use one trapezoid or something similar. So 120 joules of work is done from beginning here to 4 meters. So how much energy does this particle, block, object, whatever, have at 4 meters? How much energy does it have at 4 meters? Max?
380 joules.
Yeah, in this case, it's going to be 380 joules here. Because again, what did Max do? He took the starting energy of 260. He added on the 120 joules of energy it gained from this area under the curve and did 260 plus 120, yielding this 380. Yielding that 380. And why am I starting from the beginning? Why am I not doing it this way from here over? Again, because I know the velocity in the beginning. You can do it from here over, get the area, but then backtrack and start the problem over from here. Because you need to have the work kinetic energy theorem. So let's write down what we would do now. We would say the work done equals the change in kinetic energy. The work done is 120 joules. That equals 1/2 mv squared minus 1/2 mv naught squared. Final minus initial.
Oh wait, so it's not a 380 equals 1/2 mv squared.
Now what?
Not 380 equals 1/2 mv squared. I just don't understand why.
I don't know what you're saying. 3AD?
For 380.
Oh, 380. Sorry. So no, what's happening here is this. I want you guys to apply the work kinetic energy theorem, which talks about the change in kinetic energy. And the change in kinetic energy is due to how much work was done. So at this moment, I can take the kinetic energy and find the velocity from that alone, like we did earlier right here. And I can just do 380 equals 1/2 a times v squared and find the velocity right here. But I'm trying to point out how the work kinetic energy theorem is used as well. So you can do it either way, Tristan, absolutely. So Tristan is saying the following. He's saying, can't we just do 380, which is the amount of energy it has, equals 1/2 mv squared, and find the velocity, and get the velocity, and that will be the velocity at 4 meters? You can absolutely do that, but I'm just trying to emphasize the work kinetic energy theorem here. So if I look at this problem, I can see that I've got the initial velocity here, right? That initial velocity was 8. And this kind of a problem is going to come up, where you're given the initial velocity and you want to find the velocity later on. So 120 equals 1/2 8v squared minus 1/2 8 times 8 meters per second squared. And as a result, I can get v. Now, either way I do it, Tristan, I'll get the same answer, right? Whether I use the work kinetic energy theorem and solve this long equation here, or if I use the simpler approach that Tristan thought of here by just looking at the energy at that moment, we'll get the same answer for v. What do we get? What do we get when we solve either equation? 9.8. So again, what are we doing? We're we're estimating, we're approaching, we're determining the value of the velocity or speed at 4 meters. At 4 meters. So it's important to recognize that these approaches are both valid. If it were a question on an exam that asks for a quick velocity at a moment and you have the energy, definitely use this idea. If the problem, though, did not give you something about the energy at that moment, but you knew the area under the curve and you knew the starting velocity, you could find the final velocity from that. So I want you to see both approaches in this problem. There may come a time where you don't have the actual energy of 380, but you know that this area is 120. So you know that it goes from 120 in area, that's going to be the work done. If you had a starting velocity in the problem given, you could then find the final velocity, which is the velocity here at 4 meters of 9.8. The last part of the problem asks us to find the velocity at 6.5. Actually, it says speed, right? Yeah, it says speed. But at 6.5, so what am I going to have to do for this last portion? What do I have to do for the last portion to get it at 6.5? What are you thinking, Max?
Calculate the area of that trapezoid and then subtract it from 380.
Agreed. Does that make sense why we're doing the area of the other trapezoid now? So from 4 to 6.5, it's a negative integral, so therefore we have to subtract it from the energy of the system, or the kinetic energy of the object. So that area is going to be, what is that area going to be actually? 2.5 plus 1 divided by 2 times 20. Does somebody want to give me that area? They can calculate it real quick. The area I'm highlighting in green, please.
35.
What is it? 35. So in this case, negative 35. So what would my energy be at 6.5 then? I'll take away 35 from this 380 right here. So 345. That's the amount of joules it has at that moment. So again, if I want to know the energy at any given moment, find the integral and either add or subtract that integral to the previous energy you had. So as a result, the last part becomes what? See? Last part is saying find the speed at 6.5. So it's got a certain amount of energy at 6.5. And that equals 1/2 mv squared. It's got 345 joules of energy there. The mass is still 8. And V, what will it turn out to be? What is that going to turn out to be? Why do I feel like the number's off there? Plus 2 times 40, 1/2. What do we get for V in this problem, guys?
9.3.
I think I may have copied the diagram wrong slightly. So when you look at the example in the book, it's slightly different than this one, because I think my angles are off. 20, 6.5. Yeah. The idea behind this is that when you take the integral, you're gaining kinetic energy because you're doing work to the system. You can do negative work and thus obviously lose energy. Let's finish off today with one last idea. Okay, one last idea I want to point out. And this is the last chapter 7. So we pretty much went through all of chapter 7 just now. So the power, anybody remember power? What the definition of power was from last year? Close. It has to do with work for sure. Power is defined as the rate at which work is done. It's okay. It's okay. So it's a new idea. So ready? I'll give you a simple, easy example. Okay? I'm lifting weights. I take a weight and I lift it really, really, really slow. Okay? As a result, I cause a gain in potential energy. But if I lift it really, really fast, I've done the same gain in potential energy, but I've done it quicker. Agreed? So the work done over time is the definition of power. It's how quickly you do work. You could walk up and down the stairs of Loyola, right? And walk nice and slow. And it won't be too tough. But how many of you have done stairs as an exercise before? Basketball, I know you've done it. Track, have you done it? Cross country at some point? Basketball? Other sports? I'm trying to think of other. Right? I don't think we've done any soccer and baseball.
No.
But stairs are really, they're terrible, right? Because you're running up and down the stairs the whole time. So you're doing the same amount of work. You are. Because you're gaining what kind of energy as you go upstairs? Potential energy. You have kinetic because you're in motion. But again, you're doing work. And it's the same amount of work that you're doing. But you're doing that work in a faster time period. So T is smaller in that circumstance. So I might do 250 joules of work to run up the stairs in Loyola, but if it takes me 10 seconds, then I'm doing 25 watts of power. But if I do the same amount of climb and it takes me 100 seconds, then I'm only generating 2.5 watts of power. So power is really what some people call wattage. The word is not proper or correct, but it is a word that people use all the time. Especially for electrical systems, when you look at a light bulb, you look at the label when you buy it, it says, this is a 60 watt light bulb. This is a 40 watt light bulb. Watts were named after...
Watt.
Yeah, I'm just going to say. What do you think I was hoping somebody would say? Yeah, the football player. I always think of the football player, Watts. I don't know why. I don't even know who the actual first name of the scientist was. J.J. Watts? So the amount of watts generated is the physical power that you are generating. So if you can do something faster than someone else, you are generating more power. Now, I want to extend this idea. James Watt? Thank you. So it is a J. Watts, huh? I want to extend this concept of power into calculus. Rates. What do rates mean in calculus? Rates mean what? Are they integrals? No, right? Not rates. What are rates? Derivatives. So I know, I gave that one away. So the power is really dW dt. It's the rate at which work is done. dW dt. That's what power really is. The rate at which work is done. Now, luckily enough for us, we can also derive the second part of it, and it's pretty easy to derive. We think of power and dW, right? The derivative of work, dW. Work is really F cosine theta times d. But if I'm looking at the derivative, I just put a dx instead. And instead of this being over time, I think of this as dt. And what is dx over dt? What is dx over dt really? What did we just say a little while ago? What is dx over dt? What is it? Velocity. So if I want to find the power at an instant, I can do the force times cosine theta times the velocity. Our second formula that we'll use here. Okay, so these are two really important formulas to consider. We'll talk more about power because I can understand you guys didn't cover it. It's not a problem. The power is honestly really simple because all you got to know is how much work was done and then it's divided by the time period. That's the only difference from the last things we did. So if you can find work done, you can easily find power because it's just divided by time. It's just divided by time. Now, if we have a work function, then we can take the derivative of that work function with respect to time, and we'll talk more about that in the next class, so I don't go along with this idea. Okay, so here's what I'd like you to do. This is a different homework for once. Okay, I'm not going to assign problems just yet for homework. Here's what I really want you to do. I want you to read chapter 7. You've got 2 days to do it. Chapter 7 in length is not even 20 pages. It's 149 to 167. It's 18 pages. 9 pages tonight, 9 pages tomorrow. And the reason I'm not giving you word problems or any homework is to emphasize the importance of reading. I haven't really pushed too much this year. I haven't been pushing you to say you should be reading the chapters every time. I assume that you're reading the chapters, but it may not be happening. So if it were me, I would absolutely recommend reading 9 pages tonight and 9 pages tomorrow. Not 18 pages, right before class, 2 days from now, the period before. Is that clear? What I'm going to do, though, is in 2 days, you meet with Alex during first period. I'm going to have Alex go through a bunch of sample problems of these topics before you start the homework on this topic. Okay? So in your recitation on Thursday, you'll do sample problems with Alex. You'll have already read chapter 7 before that sample problems with Alex. Please, don't wait until after that. Because when you start doing the problems with Alex, you might be a little bit lost because you didn't read ahead of time. So read chapter 7, please, before then. Do problems with Alex. And then later that day, I will go over more advanced problems with you, and I'll give you an assignment for homework on it. Is that clear? Okay, then in the next class, we'll get right through momentum. So we're covering energy and momentum, which is like almost 3 chapters in your book in a couple class periods. And the reasoning is because energy you should really have down pat from last year. And this is not a topic that involves a lot of practice. It's one of the easier topics in physics, which is why I'm trying to go through it quicker so we can spend more time on the tougher stuff like rotational and simple harmonic motion and vibrations, which is a big part of your AP exam. Chip.
I was just going to ask when you're doing dw, why you're not taking the derivative of cosine?
Because theta is not a function of time. Theta isn't changing this problem.
Oh, so is it like constant?
The work is changing as a function of what time you're at. So if you generate more power, then less power, then more power, that's a function of time, which is why we take its derivative there. So that's the case, but theta is not a function of time. It's the same angle the whole time. So cosine theta is a constant, so technically it's like coming out front before you take the derivative. Okay? Again, please guys, read chapter 7. I promise it will definitely help you. Okay, it will definitely help you. All right, have a good day. I'll see you guys Thursday or after school today if you want to come by for some help. Again, I'll be here after school. Feel free to come by.
Thank you.
See you guys.
It is so difficult. One of my friends has
Okay, page 171. Oops, let me airplay, sorry. Okay. So this problem says the following. So if you have it in front of you, you can read it. I'll read it out loud, though, either way. It says, a father racing his son has half the kinetic energy of his son, who has half the mass of his father. If the father speeds up by 1 meter per second, the father speeds up by 1 meter per second and then has the same kinetic energy as his son. What are the original speeds of the father and the son? Okay, so let's start by breaking it down, thinking about variables. So it says again, a father racing his son has half the kinetic energy of his son. So the kinetic energy of the father equals 1/2 the kinetic energy of his son. That's how we're starting this problem off, right? That's what's stated in the beginning, that he has physically half the kinetic energy. Let's see. It then says the son has half the mass of the father. So when we start replacing stuff, we could say that the mass of the son is equal to 1/2 the mass of the father. So those are two statements that were given in this problem. Okay, the father's kinetic energy is half of the son, and then the son's mass, if we write it this way, is half the father, and the father is double the son. Either way you want to think about it. So clearly, what is happening here? The son must be running with a, what? Higher, lower, same? Higher speed than the father. And that's just logical, what's happening here. Okay, because kinetic energy is a function of mass and speed. So the son's speed must be greater. And our goal in this problem is to determine the original speeds of both. Okay, so this is the original scenario. What else can we write? We're then told that if the father speeds up by 1 meter per second, he'll then have the same kinetic energy as his son. So what we want to think about here is the fact that we have a new velocity for the father. So if we want to say this at the top, we could say the velocity of the father in the second circumstance is equal to the velocity the father had in the first circumstance plus 1 meter per second. That's that third statement right there. These are the first two that we're really going to have to work with, and then we'll see how the third one comes to play a role. So obviously there are two unknown variables, the speed of both the father and the son before this change occurs. So if we have two unknown variables, we're going to most likely need, two equations and your substitution or some sort of combination of equations there. So there's a good chance we want to write out this equation twice. So if we wrote it out in the beginning, we could start with using the original scenario. And we could say the following. We could say that this original equation here tells us the kinetic energy of the father. Well, that's going to be 1/2 the mass of the father times the velocity of the father in the first circumstance squared. That's the father's kinetic energy. It's 1/2 times his mass times his velocity squared. And this is in the beginning circumstance before the father speeds up. And that is going to equal, right? That is going to equal 1/2 of the sun's kinetic energy. Okay? So this is my scenario right now. And it seems to be tough because we don't have a lot of information, a lot of stuff isn't given, but we actually are given some stuff, like this right here. Right? We haven't used it yet. So what do you think we can do with this value? Or this expression?
Remove the 1/2 from the right side of the equation.
Yeah, so we could either get rid of this 1/2 by moving it over, but what can we do with these equations together is what I'm saying.
Substitute.
Yeah, substitute, right? The mass of the sun is 1/2 of the mass of the father. So let's replace that in the equation right there. Okay, so let's use this constraint or this arrangement, and let's replace that in right there for the mass of the sun. So this equation then becomes 1/2 the mass of the father times the father's velocity the first time squared equals 1/2, and I've got 1/2 mf, that's replacing ms, and then vs1 squared. Why do we do this? Why do we substitute in for ms? What does this allow us to do in the equation, Chip?
Solve for VF1s and then you can find VF2.
Yeah, we can, but before we even do that, Chip, you're definitely right. But what do we have to do first? What do we notice on both sides?
That there's the 1/2 MF.
Yeah.
On both sides, so you can just cancel it out.
The 1/2 mf on both sides. Notice, the problem is not asking us about the mass of the father or the mass of the son. It's asking us about their velocities. So the fact that the masses are dropping off is actually very useful for us here. So I see that this right here cancels with this right here. Those two things that I circled in red drop off. So that allows me to recognize that in the beginning of this problem, before the scenario had changed, this relationship exists. But again, it's not enough. It's not enough. Why isn't this enough right now? How many variables do I have? Yeah, 2 here, right? We've got both. I don't have one equation right now. So it's still not enough information for me to solve this problem. But I'm told something else. I'm told that when this occurs at the top up here, when that occurs, when VF2, the velocity of the father in the second part of the problem, when that changes and it speeds up, we're told that the kinetic energies are the same now, right? We're told that they have the same kinetic energy when the father speeds up a little bit. So, and the speeding up process is by adding 1 meter per second in. So what can we say as a result of this? Well, what we can say is the following. We could say, in the second scenario, so this is like scenario number 1, and this is like scenario number 2. In the second scenario, the kinetic energy of the father equals the kinetic energy of the son. But this is only because the father has sped up a little bit. So it's no longer equal to 1/2 of his son, it's the actual value that is equal. Well, the kinetic energy of the father itself, or himself, is still 1/2 mass of the father, but now it's times the velocity of the father in the second circumstance. Has the velocity of the sun changed at all? Did it say the velocity, is the sun getting faster, slower, or anything like that? The problem? I don't think so, right? It doesn't say it anywhere that the kid is getting any faster. So we're told that 1/2 m VF2, this is the father's velocity in the second circumstance. And we'll replace that in a moment. And what we get on the right side is still 1/2 the mass of the sun times the velocity of the sun. And I'm going to still put a 1 here because it hasn't changed. I called the velocity of the sun a moment ago VS1, the velocity of the sun in the first part. Well, the velocity of the sun in the second part is the same as the first part, so I'm going to leave it as Vs1. I'm not going to change that. Now, the velocity of the father, though, in the second part is not the same. Right? The velocity of the father in the second part is not the same. So this becomes 1/2 mf. And then the velocity of the father is Vf1 plus one more. So I'm replacing what's underlined in green with what's circled in green at the top there. Okay, we're told that the father speeds up by 1 meter per second from his initial velocity, so it's Vf1 plus that 1 meter per second. God bless you. And we still know that the sun hasn't changed velocity, and we also know that this correlation can still go in right here. Right? The mass of the sun is still half of the mass of his father. The kid isn't suddenly getting bigger, right? He's not gaining weight or losing weight as the process happens, or gaining or losing mass. So this becomes still 1/2, and then this is still 1/2 mf again, and still Vs1 squared. What cancels? What cancels? What do we notice in canceling here? Ooh, did I? I think I dropped 1/2 earlier, didn't I? Yeah. Can somebody find the 1/2 I dropped? You know why I noticed it? I started looking at the solution and I saw the 1/2 here, the 1/2 here, the 1/2 here. And I'm like, wait, that's similar to this one, right? Wasn't it a half and a half and a half? Where's the half missing from earlier? Try to find it, come on. Look at the first line. The first line stated that the kinetic energy of the father is half of the sun, right? And we started by saying 1/2 mv squared equals 1/2 mv squared. Was that the case actually? Is this correct? It's not. What should I put in?
Either 1/4 or another.
Yeah, another 1/2 on this side, because we were told that the father's kinetic energy is half of the sun. So the father's kinetic energy should be 1/2 of this. So we're missing a 1/2 right here. So that should become a 1/4, which is going to change that value there. So let's throw in another 1/2 right here. All right, it's half of it. And then it gets to be another 1/2 right here, which makes this inherently 1/4. This is something that, although seemingly simple of a problem because we're just looking at kinetic energy, can get very confusing with all these subscripts. And the way I recognize things when I'm doing stuff, and if I were taking an AP exam and doing this problem, I noticed that this problem really didn't change at all. The only thing that changed was adding this 1 in, right? So how could this equation be the same as, or be true if this equation is true if I suddenly add a 1? That doesn't make sense. I can't add a 1 over here and say that it's still equal to the same exact expression as earlier. It didn't change at all. So I knew that something must have been missing from earlier on the right-hand side of the equation. Because I can't just alter this and put a +1 and assume it's going to be the same thing. So that's where I recognize, oh wait, I forgot that value there. Because there's no way that equation works out. So now what happens is that this 1/2 mf cancels with this 1/2 mf right there. That equation then becomes Vf1 plus 1 quantity squared equals 1/2 Vs1 quantity squared. And now I'm going to circle in, I don't know what color, I guess I'll use blue. I'll box in the 2 in blue that are important. So we've got that relationship and we've got that relationship. So what we're doing in the process of this problem is going through the steps to come up with a system that we can then solve. And although the system looks tricky, it's really not that difficult to solve the system. Why is it not that difficult? Because one of two things. You can use substitution method, and you can easily solve for one of these two, which already kind of is done, and plug into the other. No need to distribute this right off the bat. Or you could somehow make this a 1/2, right, by just multiplying this whole equation by 2. I'm going to make this 1/2 Vs1 squared, and that's 1/2 Vs1 squared. So if you multiply this by a 2, you could set this with a 2 in front of it equal to this over here on the left side. But the key to the problem is to recognize what's going on, and it's a bit of a wordy problem. That's what makes it trickier than the beginning part. Okay, so let's go ahead and take that value. So let's do this. Let's take this equation. I'm going to double this equation on both sides. And as a result, this equation now and this equation can be combined because they're both equal to 1/2 VS1 squared. We've got a 1/2 VS1 squared in both circumstances. So I can set the left-hand sides equal to each other. I can set the left-hand sides of both equations equal to one another. And we'll get VF1 plus 1 squared equals 2 VF1 squared. What kind of an equation is this going to yield? Kind of an equation is this going to yield? I'm thinking what kind of an equation we have. Chip?
Quadratic.
Yeah, this would be quadratic. Okay, again, because we've got VF squared here, we're going to have to FOIL this out a little bit. So we'll definitely get a quadratic in this problem. Now, the other option is to take the square root of both sides, right? We can take the square root and put this as a radical 2 right there. And if we take the square root of this side, this becomes VF plus 1. That works also instead of taking a quadratic into play here. So you can make a quadratic by FOILing it out and then solving, or like I'm saying here, we square root both sides. We get VF1 plus 1 equals the square root of 2 times VF1. And square rooting both sides. By square rooting the left side, it drops the square. By square rooting the right side, it drops this square. And you have to take the square root of the coefficient also, because we're square rooting both sides of the equation. We're doing that, and we're doing that. Okay, those red square roots there are being taken on both sides, so the 2 needs to have a radical to it. And then we can solve for VF1. So I'm going to move the VF1 over. See, we get 1 equals radical 2 VF1 minus VF1. I could factor VF1 out of this equation. Right, factor out a greatest common factor. VF1 is in both spots. Take it out front, leaving behind a radical 2 here, and a minus 1 left behind there. And then solve for VF1. So this is the velocity of the father in the beginning. And that's the exact solution. No approximation needed here. If we want approximation, we do 1 divided by 0.414. This should be 1.414 minus 1. The process that you undergo here is the trickier part, not the actual algebra toward the end. This, from here down, shouldn't be that bad. It's the stuff in the beginning of the problem that's probably the tougher part of this problem, not the ending part, because now you're just doing a bit of algebra to solve. What would you do to get VS1 then? The sun's initial velocity. Where might you plug that back into?
All the way at the top, right?
Yeah, somewhere, right? Somewhere toward the top, and I'm looking for VS1. So if I were to plug it in all the way up here, it won't work, because that'll give me the father's velocity at the end.
You do the first blue.
Yep, boxed. Very good. I would probably plug it in right there and then solve for VS1. Okay, it's nice because it's going to be a square, and you're going to square this out, but you're going to have to take into account that your denominator is squared now in parentheses. Okay, and you can solve for VS1. What will that turn out to be for VS1? Let's see. This will become 1 over root 2 minus 1 quantity squared equals 1/4 VS1 quantity squared. Because I'm looking for VS1, I can take the square root of both sides. That gets rid of the squares on both sides, but the 4 we have to take into account. Becomes 1 over root 2 minus 1 equals 1/2 VS1. Again, I'm taking the square root of both sides at the same time. The square root of the 1/4 becomes a 1/2. So then to get the sun's velocity by himself, multiply by 2, which puts a 2 in that numerator. Okay. What else? Let's look at the next one. I wrote it down, sorry. Let's look at number 12, a little bit more numerical than this one was. This one was more variable, right? Let's look at number 12, which is more number-based. So number 12 we've got here on the same page. We can see that it's newtons because the slope of the line gives us joules over meters. And joules over meters is a newton by definition. Okay, and we can see that literally from the actual units here of joules and meters. Okay. Again, the integral of work, or integral of force is work, so the derivative of work is force, That's part A to the problem. Okay, part A. Let's see. It says next, if the can had an initial kinetic energy of 3 joules, moving in the positive direction on the x-axis, what will the kinetic energy be at the end of 2 meters? At the end of 2 meters. So it says initially, this is part B now. It starts initially with kinetic energy initial of 3 joules. And the question is, what is the kinetic energy of this at the end of the 2 meter runway? So that's just KE final practically, and we haven't been using F for final, so I'm just going to leave that for now. So our goal is to figure out the kinetic energy, and I'll put an at symbol and make it nicer. The kinetic energy at 2 meters. So this is a very easy problem, the second part, but it seems that it could be misconstrued. Okay, and I think that's why this problem is rated as like a level 2 in your book. Because when I read it, like, this is actually pretty easy, but I could see where the miscommunication or misconstruction comes from here. Anybody got the answer right away?
Could you just do force times distance? And so instead of doing, well, kinetic energy is equal to work, which is also equal to force times distance. So you could do.
You got the force.
3 newtons times 2.
So how much energy do you gain?
3. Or 6.
6?
Yeah.
So what would the kinetic energy be after 2 meters then? It'd be 9, because you started with 3 already? So the common misconception here is that people see this curve and think to integrate the curve and find the area under it. But this is not a force distance curve, right? So the common misconception would be to find the area underneath this curve and say that, oh, that's the amount of work that's going to be done. But it's not. Remember, the work done in this problem is literally the amount of work at the end of this curve. This graph is a graph of work done over distance. So after 1 meter, 3 joules of work were done. After 2 meters, 6 joules of work are done. So it's just going to be the 3 joules it had to start with, plus the 6 joules that are done over the 2 meters, yielding 9 joules. So, Chip, you're right, but you don't even need to do force times distance, right? The graph shows it. The graph shows that after 2 meters have gone by, the work done is 6 joules. So that's just adding 6 joules on to the original amount of kinetic energy that it had in the beginning of the problem.
So would it be like the integral? Could you also look at it as the integral of?
Yes, of your.
Going from 0 meters to 2 meters, but then also adding the initial 3 meters.
Here, I'm doing it for you so you can see it. If you had this graph, Chip, which is what's really happening here, it's a constant force, isn't it? Then you could say, oh, the work done is the integral of this. But what's the integral of that? So 3 times 2, which is really just back to 6. So if you want to think of it as an integral, the work done would be the integral of force. But why bother? You know, you already took a derivative to get the force, and then you're going to plot the force and then do the integral of that to get back to the work. That'll work, you'll get the right answer, but why not just take the 6 at the end, that's the amount of work that's already been done, and put it right there. Okay? It's a great question. You could do that if you wanted to think of it that way. So again, this kind of a problem, just I wanted to iterate, or I guess not reiterate, but to demonstrate that because the work is the integral of force, the force is the derivative of work. So this might be something you want to write down and put a big circle around and put an asterisk on it, because I don't think it's on your formula sheet if I'm correct. Let me see. On your formula sheet, you've got change in energy equals work, which equals the integral force times dr, or dx. So you've got the integral part, which is up here. This is given on your formula sheet right here. But nowhere on your formula sheet, let me just make sure I'm saying this properly. Yeah. Nowhere on your formula sheet are you told that the force is the derivative of work. And you're nowhere told that force is equal to the derivative of work with respect to distance. With respect to distance. So I would recommend that you circle that, write it down, and say, hey, maybe this is something to add to your calculator as one of those extra tidbits, right? Because if you have the integral, you have the derivative there. Okay. All right, let's keep going. Let's look at example 15. Let's go to example 15, and I think we're on the same page still. Yeah, on the bottom of that page still. Example 15 has a diagram. I'm going to draw that diagram real quick. Here's the object. That's F2. That's an angle theta. That's F3. And that's F1. Okay, this is the diagram we've got. The problem says the following. The figure shows three forces applied to a trunk, an object, right, that moves leftward by 3 meters over a frictionless floor. So already, delta x is going to be negative 3 meters, or my distance traveled is going to be 3 meters. Okay, my change in position is to the left 3 meters, or I can say my distance traveled is 3 meters because I'm using the absolute value there for distance. We're told that the forces are given as the following. F1 is 5 newtons. F3 is 3 newtons. F2 is 9 newtons. And theta is 60 degrees. So part A says, during the displacement, what is the net work on the trunk by the three forces? What is the net work? Now, you can find the overall force from all of these forces applied in the x direction and then multiply that by d. And that works. And I think today with Alex, you did something like that. And then you could also just find, if you want, the work done separately by all three forces and sum them together to find the net work. Either way works. I'm going to show you both of these methods. So for part A, again, we could start by finding net force, or we could find net work. Let me show you what I'm getting at here. So, we've said that the work done is really the amount of force times distance times cosine theta, right? What is that theta in these problems? What is theta by definition? It's not just some arbitrary angle, it's specific in the circumstance. For work, theta is the angle. Say again? It's not actually, Chris. That's a good stab at. Though in this case, it looks like it is, but that's not the general assumption of it.
Between the vectors of f and d.
Very good. The angle theta is between the applied forces and the direction of motion. Write that down, please. Theta is the angle between the applied force and the direction of motion. This is why in your formula sheet it's written as a dot product. Okay, it says F dot D, or it says F dot R, I think, on your formula sheet. It's much, much easier to remember that it's F cosine theta. Okay, again, your formula sheet says F dot R is what they're saying here. But we are going to be recognizing that it's not F dot R. So I'm going to start it first by finding the overall work done, by finding work for each of these separately. So method number 1 will be on the left. Okay, by finding work for each object, or from each force. So the work due to object 1 is going to be the force of object 1 times the distance traveled, d, times the cosine of the angle between the force 1 and d. What is that angle? What's the angle between F1 and d? What's the angle between F1 and the direction of motion? What is it going to be in this problem next? 0 degrees. The F1 vector is to the left. The object is moving to the left. So both the displacement and the force are drawn in the exact same direction. There's D right there with a dotted line I'm drawing. That's the direction of motion. So this angle theta here is 0 degrees. So the work done by object 1 is actually pretty simple. It's just 5 times 3, or simply 15 joules. That's the work from object or force number 1. I'm going to do each of these works one at a time, and then we'll just add them together. How about the work done by force 2? It's going to be the force 2 times the distance traveled times the cosine of some angle. So really, it's really about what is the angle, right, that matters here? What do you think? Chip?
We could do 60 and then, no.
You could if you did something else with the problem.
You could do 150.
Okay. So should it be 60? Should it be 150? When should it be 1? When should it be the other? What should you do?
60 times 1.
Okay. Did you hear what you said? It's not out there. He said you could use 60 as the angle, and then recognize that since it's pulling back, it's a negative work done. So you could absolutely do that. Or you could just use the angle between the force and the direction, which is 120. And then the cosine of 120 is definitely going to be a negative quantity, which will show us that the work done by the second force is impeding motion. Again, here's the object. It's moving this way. The other force is pulling back against it. So it's going to be doing negative work to the object. So I'm going to use cosine of 120. And the cosine of 120 is really the negative cosine of 60 from your pre-calculus knowledge. So we've got 9 newtons times 3 meters times either, again, cosine 60, but then put a negative in the front, or cosine 120. Cosine 60, isn't that 1/2? Right? 1/2? So this would be negative 1/2. Because the cosine of 60 is 1/2, so the cosine of 120 is negative 1/2. So we've got 9 times 3 is 27. 27 divided by 2 is 13.5 with a negative sign. So here's the work done by the first force. Here's the work done by the second force. So far, which is winning the battle is the first force, right? So that
Confused as to why it's 120 is that.
it's the angle between the force and the direction of motion. The force is here, the direction of motion is here.
So
It's not two same, okay? Just remember that. I'm telling you, it'll be so much easier to remember it that way. That for work, the angle theta is always between the applied force and the direction of motion. Again, another thing to maybe jot down, right? When we talk about jotting down all these extra things. Okay? So, right now, it looks like, again, the first force is winning the battle. More positive work is being done than negative work. How about that third force, F3? How much work is F3 doing? How much work? 0. 0, 0, 0. Because what's the cosine of 90 degrees? 0. Think about it, logically. If I'm moving this way and the force is up or down, that is not affecting my lateral motion at all. So I'm not doing work horizontally. So because we're looking for the net work done on this object, we're looking horizontally here. There's no work being done vertically because it's not moving a distance vertically. It's only moving a distance horizontally. So the applied force F3 does nothing in this problem. So my answer is simply 1.5 joules. Again, if I want the total work, I take the sum. Object or force 3 does not apply or do any work to this system. Max.
What's the point of knowing work?
Work will allow you to then see how much velocity you have later due to your work kinetic energy theorem. Work will also allow you in about, a couple sections in chapter 8 to see how thermal energy loses work or causes a negative loss in energy in the system. So if there's an object moving and you know the force and air resistance and you know the distance traveled along a curved path for a projectile, you can find out the delta E or the thermal energy lost for the system to see how much kinetic energy you have at the end to then determine the velocity upon impact. So work, for the most part, is really important when there's an external force applied or when there is some sort of loss of energy due to friction. That's the real reason we're going to do work. Okay, good question. Please ask those questions, guys. Again, object or force 3 doesn't do work. Sometimes vertical forces will do work. When will a vertical force do work? When will a vertical force do work? When it's moving? Anywhere but horizontally, meaning when it's moving? Vertically, yeah. If an object is moving vertically, and there's a vertical force applied or a force at an angle, the vertical component will do work. Like when gravity does work, you read about that last night, when an object is falling, gravity does positive work because it increases the velocity. But when an object's on the way up, what kind of work does gravity do? It does negative work because gravity is slowing down the object. If you're speeding up, you're doing positive work. If you're slowing down, you're doing negative work. Another thing that you might want to keep in the back of that brain. Chip in the back.
So the word, is it distance or displacement?
It's distance, actually. It's not displacement. It's distance. It's D for distance. So if an object follows a curved path as it's falling to the ground, and you know the force of air resistance, you can multiply it by the arc length, which is the distance traveled, not the direct chord from here to here. You see what I'm getting at there? So you would need to literally know that curved length to know how far the work, or for how many meters the force is being applied. It's the curved length. So it's always the path taken when it comes to a non-conservative force such as friction. Okay?
So it's like the free fall would probably be what like kinematics goes into this. Or like,
So, say what that?
so like a problem with work that has to do with free fall, and that's even like kinematics.
You can do it either way. It's up to you. Yeah. So you're going to notice in the AP exam that you're going to have some part 2 questions that you can use kinematics or energy methods. Either will work. Now, I think energy methods are far easier once you get used to them a bit more. And that's what Chapter 8 is going to be about. Chapter 8, we're going to really focus on potential energy a bit more. Then we're going to look at conservation of energy also. This chapter is more about work, kinetic energy, and then the concept that work is an integral of force. That was the gist of this chapter. With Chapter 8, we're actually going to start Chapter 8 next class. We're going to do a lab or 2 on this topic. I have a couple labs planned for you guys for this one. And then we're going to finish Chapter 8. Your next test will probably be like Chapter 7, 8, and maybe part of the next chapter on momentum. Okay, we'll see where we get to depending on where it is. Let's take a look at the other way to do this now. So we could do it by finding the work done, or we could find the overall force acting in the x direction first, and then just multiply it by 3. So if I think about work, right, the sum of the work, or the net work, would be the net force times the distance. If I want to find the work done on the x-axis, I could find the net work along the x-axis times the distance it's applied for. And if I want to find the net force, I know that we've got what it looks like here as 5 newtons. And what I'm going to do here is this. Take a look at what I'm doing here. I'm going to consider this direction to be the positive x-axis for now. Okay, simply because I'm looking at distance and I want my forces to work out. And since my first force, F1, is going in the same direction as distance, that's positive work. So I'm going to consider it to the left to be positive along the x-axis. Forget this displacement from earlier if it confuses you. I've got 5 newtons pulling left. Subtracting from that, I've got 9 newtons times the cosine of 60 pulling back. And that's going to be times 3 meters. So this will give us, give me another minute, 9 times cosine 60 is 4.5. This will give us 0.5 newtons as a net force times 3 meters. And 0.5 times 3 is 1.5 joules. Again, indicating that the answer doesn't change whether I look at the net force by net work or look at the net work done by looking at the net force. Either of these ways is acceptable. You can choose which you want to. Why didn't I care about the vertical component of F2? Why didn't I care about F2 sine theta, that vertical component of F2? It's not moving up or down. The work is done only left to right, so I care about the forces acting only left or right. F3 is also up and down, so F3 does not matter either. Okay? The other problem that I did want to get to that we kind of ran out of time, so I'll just tell you which one I wanted to do. After 15, I wanted to also look at 20 and 38. Okay, so here's what I'm going to plan on doing. Next class, I want to finish 20 and 38. I want to start chapter 8. I want to then go into a lab in the following class. I want to continue into chapter 8. The 7 and 8 are really together. The fact that this book splits them up is ridiculous. It's the same topic. It's all energy. So we'll do all that together. So what I need to do, though, still is give you guys a bit of a homework assignment that you haven't done yet. So here's my homework assignment for you over the weekend for now. I'm going to give you a couple problems to practice, but I want you to read chapter 8 over the weekend. Okay, so you have 3 days. You're going to have chapter 8 to read, and I'll probably send you, like, maybe, I give you the multiple choice sets. Maybe I'll start with that for chapter 7. So read chapter 8, I'll give you a multiple choice set for chapter 7, and then next class, I'll give you the word problems or the math problems for chapter 7 that I want you to practice. Okay, that makes sense? Okay, and we're going to do 2 labs for this topic. Okay, we're going to use those, remember those launchers you guys built? Remember the launchers you built back weeks ago, right? We'll use those to talk about elastic energy, potential energy, kinetic energy, and conservation. And then we're going to use like a loop-to-loop or a ramp to talk about how energy changes that way. Okay? All right. I am not after school today for